This train crosses the Sahara Desert. Join us on an epic journey aboard one of the longest trains in the world. Spanning 2.5 kilometers and crossing 704 kilometers of the unforgiving Sahara Desert, this engineering marvel braves scorching temperatures, shifting sands, and extreme conditions to transport vital resources. Discover the incredible feats of technology and endurance that make this railway a lifeline in Mauritania. The Sahara Train. This train embarks on a 704 kilometers journey through the Sahara Desert, enduring temperatures as high as 48 degrees Celsius. Located in Mauritania, it carries iron ore extracted from the mines in the Zouerate region. Its destination is the port city of Nouadhibou, a 20-hour trip. To maximize efficiency during this long journey, the train connects as many wagons as possible, reaching lengths of up to 2.5 kilometers. It is one of the longest trains in the world, hauling over 17,000 tons. But how do the locomotives withstand extreme heat and desert sand? How do they pull so many wagons? And how does the train operate on a single track, crossing others? What happens when the track gets covered in sand? Construction of the railway began in 1960, following Mauritania's independence from France. The project was funded by a consortium involving France, the United Kingdom, Germany, and Italy, with Mauritania holding only a 5% stake. Operations commenced in 1963, and by 1974, the Mauritanian government had acquired full ownership. The railway was built to transport iron ore from the country's largest mines in the Zouerate region to the port of Nouadhibou on the Atlantic coast. By 2020, this railway alone accounted for 11% of the nation's GDP and 43% of exports, according to a report by SNIM, the railway's operator. The number of wagons can vary, but in configurations over 2.5 kilometers long, there may be 200 to 210 cargo wagons, 1 or 2 passenger wagons, and around 10 additional wagons, such as tankers for liquids or flatbeds for vehicles. On average, the train hauls 17,640 tons of cargo. Mauritania's mostly flat terrain helps ease the locomotive's workload. Even so, moving such loads often requires 4 3,300 horsepower locomotives, 2 4,500 horsepower locomotives, or a combination of both. When multiple locomotives are at the front, they are linked by electric control cables and pneumatic brake hoses, all controlled by the crew in the lead locomotive, typically just a driver or a driver and an engineer. If additional locomotives were at the rear or middle, they would be controlled via radio, but this is not the case for this train. The locomotives used by this company are diesel-electric. A diesel engine powers a generator, which drives AC electric motors with immense torque. Fully loaded, the train travels slowly, averaging speeds below 50 kilometers per hour, a slow and steady approach. In 2010, the company acquired 6 new 4,312 horsepower diesel-electric locomotives, increasing their fleet to 44. Each locomotive features a 16-cylinder, 2-stroke diesel engine connected to an alternator, and 6 AC electric traction motors, 1 for each axle. These locomotives can reach speeds of 113 kilometers per hour on their own, impressive for a vehicle weighing as much as 190 cars. A locomotive built for the desert. This model comes with special modifications to operate in temperatures exceeding 50 degrees Celsius and withstand the fine desert sand, which can cause significant wear. It's the EMD-SD70 ACS, where the S stands for sand. The locomotive features a downward-facing radiator that draws in air from the surroundings and expels it through fans mounted on top. The fan blades are coated with a special erosion-resistant paint to counteract the effects of the sand. This air cools the radiator and, in turn, the engine located in the center of the locomotive, while also cooling the dynamic braking system. The dynamic braking system works by using the traction motors as generators when the locomotive slows down. This system is not regenerative, meaning it does not recover energy. Instead, it is rheostatic, where the energy is dissipated as heat through large resistors cooled by the air mentioned earlier. Since this train rarely operates under braking conditions, This system offers a better cost-benefit ratio than a regenerative one. Additionally, it reduces the use of the traditional friction braking system, extending its lifespan. To adapt to desert operations, the locomotive is equipped with large air filters featuring a special two-stage system. In the first stage, the filters remove fine sand and particles from the air, which is then used for engine combustion and cooling alternators, motors, and other sensitive components. In the second stage, air jets periodically blow out the accumulated sand from the filters to keep them clean. To minimize sand intrusion, all compartments are specially sealed. Gear systems are fitted with labyrinth seals, and the locomotive's body is pressurized. Unlike most locomotives, which use a sand drop system to prevent wheel slippage, this model must also deal with winds that can completely cover the tracks with sand. To address this, it has two fixed sand plows and one movable plow in the center that can be lowered if the driver notices excessive sand on the tracks. The first units of this locomotive model were ordered by Saudi Arabia in 2009 to operate in similar desert conditions. The version used in Mauritania is a variation of the EMD SD70As, which lacks the large specialized air filters. For comparison, an older model, the EMD SD70 Mac, can be seen with a much smaller radiator, reflecting the advancements in design for desert conditions. Mauritania's railway. 6 trains run daily along Mauritania's railway, 3 loaded and 3 empty. However, the railway consists of only a single track. To accommodate traffic in both directions, there are 9 sidings along the line where empty trains pull aside to let loaded ones pass. The railway also features 6 maintenance stations spread across its length. Once a day, 2 or 3 passenger cars are attached to the train, shortening the journey by about 500 kilometers compared to traveling by road. If you're lucky, you might get an actual passenger car, but more likely, you'll find yourself in repurposed cargo wagons with small holes serving as windows. These cars are overcrowded, often carrying more than 75 passengers in spaces meant for 25. Imagine the journey through the darkness of night or the scorching heat of the day. Many families rely on this railway for trade, transporting goods such as fish from the port to remote desert communities. However, economic hardships push many to ride atop the wagons rather than pay fares ranging from $3 to $10. The ride is grueling. Passengers endure constant noise and vibrations, iron dust, sand whipping their faces, and extreme temperatures, up to 48 degrees Celsius during summer days, turning the metal wagons into ovens, and as low as 14 degrees Celsius on winter nights with piercing winds. Tragically, fatalities are common as people risk jumping between wagons while the train is moving, especially when slowing down causes the wagons to collide. Even animals are transported this way. Choosing the right wagon is crucial. Because the train is so long, passengers on wagons near the rear may end up walking over a kilometer to reach the station after disembarking. The primary purpose of the railway is transporting ore, a task suited to such a massive machine navigating the unforgiving Sahara Desert. Why trains instead of trucks? Let's compare trains and trucks for freight transport. On average, a truck can move 1 ton of cargo for 51.6 kilometers per liter of diesel. In contrast, according to a report by the U.S. railroad company CSX, a train can move 1 ton for 190 kilometers per liter, making trains about 3.7 times more efficient than trucks. For instance, Mauritania's trains often use 2 4,500 horsepower locomotives, totaling approximately 9,125 horsepower. Compare this to the Volvo FH16 758 x4, one of the world's most powerful trucks with 750 horsepower, capable of hauling 250 tons. Moving the train's 210 wagons would require about 70 of these trucks. Using standard trucks, this number could easily double. Now, consider the power-to-weight ratio. A truck needs 3 HP per ton. A train requires 0.5 HP per ton. With 4 3,300 horsepower locomotives, 13,383 horsepower total, the train would need just 1.3 HP per ton. Trucks also require roads, which have significantly higher maintenance costs than railways. While road costs can be offset by shared traffic, constant speed changes reduce truck efficiency. Desert roads face additional challenges, such as being buried by sand. Trains benefit from reduced air resistance due to closely spaced wagons, while each truck faces significant drag. Additionally, train wheels experience much less where compared to truck tires on asphalt. Maintenance for train suspensions and wheels is also lower than for trucks. Lastly, operating a train requires just one engineer and one conductor, compared to the 70-plus drivers needed for trucks. Intermodal transport, the best of both worlds. While trucks have advantages, such as the ability to navigate irregular terrain and reach nearly any location, they cannot match the efficiency of trains over long distances. This highlights the importance of intermodal transport, where the most suitable method, rail, road, river, or air, is used for each segment of the journey. This approach minimizes costs and maximizes efficiency. Well, that's it for this video. What did you think about this 2.5-kilometer long train crossing 704 kilometers through the Sahara Desert? Don't forget to like the video and subscribe to the channel. Big hugs, and see you next time.